Alright, so let's see. A dam is used to hold back a river. The dam has a height of 12 meters and width 10 meters. So height 12 meters, width 10 meters. Assume the density of water is 1000 kg per meter cube. Determine the net force on the dam. Why does the thickness of the dam increase with depth? Okay, so you saw that at the top of the dam the pressure is atmospheric pressure P0, and as you go deeper in the water the pressure increases. The pressure as a function of depth is given by, and all right, so we'll use this notation. Y is measured from okay, Y is measured from the bottom. Okay, so, and we'll call H is measured from the top. Okay, so the pressure at a depth H is given by P0, the atmospheric pressure, times rho, the density of water, G times H. Okay, and all right, so let's see. Now, so this is atmospheric pressure and plus that. Now there's atmospheric pressure here as well. So this factor is cancelled by the atmospheric pressure on this side. So the net force is just the force due to the column of water to the right. Okay, so the net force at a depth H is equal to P minus P0, which is the gauge pressure, times dA, where A is the, so this is the force on this strip of the dam, okay, and that's the area of that little strip. All right, so the net force, and we will integrate this, is rho GH dA, and dA is width times dy. Okay. All right, so now let's we'll integrate over y, and so h is so let me write rho gh. H is capital H minus y w dy. Okay. All right, and so the net force is integral of df net okay, and I'll go to the next page because I want a little more space. So okay, and so the net force is rho, and this is equal to that, so rho gh minus y w rho g w h minus y dy, and of course y goes from 0 to h. Okay, so y goes from 0 to h. Okay. All right, so let's do this integral. So this is rho g w h, that's a constant factor, minus rho g w y dy. Okay, and this would be rho g w h times y minus rho g w y squared by 2, and evaluated at between 0 and h. Okay, so this this factor will give you h minus 0, which is okay. So the first term is w g rho g w h squared and the second factor is rho g w h squared by 2. Okay, so net rho g w h squared. Okay, so let's give this let's write it more sensibly. So this is rho g h by 2 times wh. Okay, and the reason I write it like this is so this is the net force. Now here's the answer, and I'm trying to make plausible, trying to make sense out of this answer. Now you'll notice this is the area of the dam. Width times height is the area of this face, and the net force is the area and times this is the pressure at the half the depth of the dam. So, and that makes sense. This is average pressure times the area, which is the net force on the wall of the dam. Now we still have to answer part B. And page below. Part B. Okay, so this is part A. Okay, notice that the force on this strip is given by that. Okay, and or rather we'll write it like this. So the force on this strip is given by rho gh w dy, and as the height increases, as the depth increases, this force increases, and so the thickness of the wall has to increase. Okay, so that equation tells you why the thickness of the wall has to increase, and you can see that the force is increasing linearly with depth, and the thickness is increasing linearly with depth. So dF, the force, okay, let's draw dF, and this is H, is dy. So, and as we said, since the force is increasing linearly with depth, the thickness has to the wall has to increase to counteract that force. And so that's it. Okay. So that takes care of that problem.